A digital twin is a dynamic virtual representation of a physical asset, system, or process that is continuously updated using real time data. Unlike traditional simulations, a digital twin is not static. It evolves with the physical counterpart throughout its life cycle by integrating sensor data, operational history, environmental inputs, and performance metrics. Now, why do we need digital twins? Modern engineering systems are becoming increasingly complex. From smart factories and autonomous vehicles to power grids and aerospace systems, traditional monitoring and maintenance strategies are reactive or scheduled. These approaches often lead to unplanned downtime, suboptimal performance, and higher operational costs. Digital twins enable predictive insights, real time optimization, and risk mitigation. They reduce uncertainty in decision making and improve life cycle management. In high value industries such as aerospace, energy, automotive, and manufacturing, even marginal efficiency improvements translate into significant economic gains. That is one of the core drivers behind digital twin adoption. Let's now look at how digital twins work. A digital twin architecture typically consists of five key components. First, the physical entity. This could be a machine, turbine, production line, building, or even an entire city. Second, data acquisition systems. IoT sensors collect real time data such as temperature, vibration, pressure, flow rate, structural strain, or operational state. Third, data communication infrastructure. This enables secure transmission of data to cloud or edge computing platforms. Fourth, the virtual model. This is a high fidelity computational model that may include physics based simulations, CAD models, system dynamics models, or hybrid models. Fifth, analytics and intelligence. This layer processes data using statistical methods, machine learning, and AI algorithms to generate insights. The synchronization between the physical and virtual systems is continuous. As new data flows in, the digital twin updates its state, allowing engineers to monitor conditions, simulate scenarios, and predict outcomes. Now let's discuss the types of digital twins. Digital twins can generally be categorized into four levels. Component twins. These represent individual parts such as a motor, valve, or battery cell. Asset twins. These model complete assets composed of multiple components, such as an engine or robotic arm. System or unit twins. These represent interconnected assets working together, like a production line or power substation. Process twins. These model entire operational processes, such as supply chains, manufacturing workflows, or smart cities. The level of abstraction depends on the intended use case and system complexity. Now, the role of artificial intelligence is central to unlocking the full potential of digital twins. AI enhances digital twins in several ways. First, predictive maintenance. Machine learning models analyze historical and real time sensor data to predict failures before they occur. Techniques like anomaly detection, time series forecasting, and remaining useful life estimation are commonly used. Second, performance optimization. Reinforcement learning and optimization algorithms help determine ideal operating parameters under varying constraints. Third, anomaly detection. AI can identify subtle deviations that traditional threshold based systems might miss. Fourth, scenario simulation and what if analysis. AI models can simulate operational changes and predict system responses under different environmental or load conditions. Fifth, automation and closed loop control. In advanced systems, insights from the digital twin can automatically adjust the physical system through feedback control mechanisms. In essence, AI transforms the digital twin from a monitoring tool into an intelligent decision support system. Now let's explore real-world applications. In manufacturing, digital twins enable smart factories. Engineers can simulate production lines, optimize throughput, and detect bottlenecks before implementing physical changes. In aerospace, digital twins of aircraft engines are used to predict component wear, optimize fuel efficiency, and enhance safety. In energy and utilities, power plants and wind turbines use digital twins to optimize output and reduce downtime. In automotive engineering, digital twins assist in vehicle design validation, battery performance monitoring, and autonomous system testing. In construction and smart infrastructure, digital twins of buildings enable energy optimization, structural health monitoring, and life cycle management. In healthcare, patient specific digital twins are emerging for personalized treatment planning and medical device.